Yeah. Okay, so I missed the introduction here, but nevertheless, I was saying that today Bruno is presenting about probing quantum chromodynamics with heavy ion collisions. So thank you, Bruno, for accepting our invitation. Please feel free to start your talk whenever you're ready.
Okay, well, thank you for the introduction. Yeah, it's great to be back here. So today, the title of my talk is Probing Quantum Chromodynamics with Heavy Ion Collisions. But since I expect very few of you will be QCD experts, QCD is quantum chromodynamics, I'll spend roughly the first half of the talk introducing QCD and discussing essentially why it's interesting, what we know about it, what we don't. And then hopefully in the second half of the talk, I'll discuss properly heavy ion collisions, QCD at finite temperature, and so on and so forth. So please feel free to interrupt me at any point if you have any questions whatsoever. I'll do my best to answer them. Disclaimer, if you are a QCD expert, this will be boring. So, you might switch off and come back in 20 minutes if you're a QCD expert. Okay, so first things first. This is the standard model of elementary particles that that physicists more or less agree on. That's what we see and observe in the universe. And this set of particles is a highly predictive theory that essentially explains everything that you see on this Earth. Not everything that you see on the cosmos, of course, because you have then dark energy and dark matter. But as far as ground-based experiments go, this is more or less it. Now, if you're only asking about ordinary particles, say, or everyday particles, I should say, like electrons, protons, neutrons, stuff that make up atoms, you would only pay attention to those 5 particles there. So the up and down quarks, and the gluon, which together make up protons and neutrons, which give you atomic nuclei, and the electron and the photon. I've also just dimly marked the Higgs because without the Higgs, the electron wouldn't have a mass. But assuming that the electron does have a mass, you'd also be fine just looking at the electron and ignoring the Higgs. Okay, so that's what essentially gives rise, after, so of course, some complicated calculations, to everyday condensed matter, to the sun, to all physics that you know of in the solar system, except neutrinos, which are down there, which I'll not discuss today. Okay, so what do we understand by QCD? QCD is the theory of essentially of the strong nuclear force. And again, I've highlighted the relevant particles for QCD. So essentially all of the quarks plus the gluon, which is just like the photon in electrodynamics, is the particle that carries the force between these particles and makes them interact. It's conventional to distinguish them into groups divided by their mass. So if you look at the up, down, and the strange quarks, one usually calls them light quarks because they're light compared to in mass. Here the masses are given in mega electron volts. They're light compared to a scale that that I'll mention in a few minutes. Then you have the heavy quarks, which are the charm at the bottom quarks, which are the C, also denoted by C and B. They're heavy in the sense that, for instance, if you look at the mass of one of the quarks, say it's above a giga electron volt, and that's already beyond the mass of the proton or the neutron. So that's, again, for reasons that will become clear in a few slides, that's heavy. And then you have the top quark, which usually we don't discuss in a QCD context because it's so massive, it interacts very strongly with the Higgs boson, and therefore it interacts strongly with the Z and the W bosons, and it decays much quicker than the QCD typical timescale. So we usually ignore the top quark when discussing QCD. So we'll just focus mostly on the light quarks, and at some points on the heavy quarks, which are the charm on the bottom quarks. So, okay, this is the setup.
Sorry, Bruno.
Yeah.
We're already mentioning the masses as a criteria to
Yes.
to divide the theory. Is the origin of the mass part of the story, or?
Yes, their masses, as they're tabulated there, they come from the Higgs, as we know them, but most of the mass of the particles that you see on day-to-day basis, say the mass of the proton or the neutron, is due to some complicated dynamics, which is not yet very well understood, given by the interaction between gluons and up and down quarks. Yeah, so does that answer your question? Do you have any?
Yeah. So those values that you're giving there, are they what?
Okay. So you're getting technical to begin with. They're in some way of writing down the theory. I don't want to get into technical details of renormalization and regularization, but in some way of writing down the Lagrangian of the theory, these are the parameters that appear that symbolize the masses of the quarks in the Lagrangian. Again, if you've taken a quantum field theory class, you'll be familiar with concepts such as renormalization. I'll not discuss these in detail, but if you have taken such a class, you should be able to figure out what's what. And please, ask questions if it's not clear. Good. Okay, so just let me give you, again, because I don't expect you to know QCD, let me give you I'll spend 2 or 3 slides essentially showing you how do you write down the theory. I'll stop more or less about there, but I still think it's important that you get to know what we're talking about. So you'll usually hear in particle physics the word SUN or UN or other labels for groups. And well, in this case, what you need to know about SU3, which is the symmetry group that defines the theory essentially, is that it's the group of 3x3 unitary matrices with determinant 1. And as such, you can write them in terms of a set of generator matrices, the TAs here, which you can choose them to satisfy some normalization condition. And if you like group theory, then you also know that the algebra that these matrices satisfy is given by commutation relations, given by, well, the commutator of TA with TB, it will be I times some set of structure constants known as FABC times, again, another generator matrix. So this, and well, to be very concrete, so that you don't think that I'm just defining some abstract algebra, you can write them down. You can write down a set of matrices that satisfy the above, just like you do with the Pauli matrices. In fact, if you look closely to these matrices, you'll see that by blocks, they very much look like Pauli matrices. It's just all of the ways in which you can essentially generate rotations in terms of unitary transformations. And that's it. These are called Gell-Mann matrices. Okay, so now just a slide on what the theory is. So it's a quantum field theory where you have a gauge field which is called a mu, which is matrix valued, as opposed to in electrodynamics where you have a gauge field which is a number, and then you have some matter fields that are also that are vectors in this 3x3 that are acted upon by these 3x3 matrices. In the definition of the theory, of course, I could either have chosen to present this historically, how we arrived at this, but I'm choosing to present this as what we know about it now, and then later I'll discuss some historical aspects. But what we end up at the end of the day with is that these matter fields and the gauge fields have certain properties certain transformation properties under the symmetry, the gauge symmetry, which is here parameterized by U. Then you can define a field strength, which is the analog of the electromagnetic field strength that contains the electric and magnetic fields, which also has a transformation property. And if you then sit down to try and write gauge invariant terms to define a Lagrangian that defines the dynamics for your theory, you'll end up with this kind of structure. Essentially, you'll have what's called the Yang-Mills Lagrangian, which is essentially the square of the field strength. This is just if I omit the index A here, this is just the same Lagrangian that you'd use to describe free photons, but you'd have to omit the last term up here in the definition of the field strength. And then down here, you have the Lagrangian for the quarks, which specifies both the equation of motion, the free equation of motion for the quarks, plus their coupling to the electromagnetic field. If this is not very familiar to you yet, don't worry about it. Well, not use this much further in what comes, but if you're ever interested in studying this, then this is your starting point. This is what you need to know. Okay, so now let me discuss aspects of this theory. So let me discuss QCD at both high energies and at low energies. So the most well-known feature of QCD, I would say, besides the fact that it leads to protons and neutrons, is that at high energies, the interaction strength becomes weaker. So if I draw down diagrams that represent a 3-gluon interaction, a 4-gluon interaction, or interaction of a gluon with a quark, these are all proportional to the coupling constant or to a coupling constant squared. And if you essentially give higher and higher energies to the ingoing and outgoing particles, either gluons or quarks, you'll find that the scattering amplitude that you can associate to this process decreases as you increase the energy. This is summarized by the QCD beta function, which is essentially telling you here dg to d log mu, where G is the coupling constant strength, so it tells you how large the amplitudes that define these interactions are, and then the log of mu here is mu here is a scale, a mass scale or energy scale, which what this tells you here is that if you increase the reference scale mu, so the typical scale at which your outgoing or ingoing particles have, say, larger or smaller energy, then the coupling constant will vary in the manner given by the right-hand side here. And if you replace what these numbers NC and F and TF are for QCD, what you find out is that this beta function is negative, so that the effective strength of the coupling decreases at higher mu and therefore at higher energies. This is very good for testing in high energy experiments. For instance, the most famous one, which provided and still provides a very good test of QCD, is deep inelastic scattering, where you hit a proton with a highly energetic electron. they interact through a photon. And if this photon is sufficiently energetic, then the proton will just break apart as a result of the interaction. And then there will be a big mess that you'll see in your detector at the end of the day. But the fact that you can understand the interaction at higher energies perturbatively essentially allowed us to determine that what you are really scattering with when you take an electron and interacts with a proton are really the quarks. Otherwise, you would still have a very complicated mess here defining the proton, and you wouldn't be able to essentially interact one by one with the electron with a quark, which then led to Feynman's famous Parton model, which essentially what the bottom line that it tells you is that you can, if you have a cross section, so how likely is it that if you throw an electron to a proton, how likely is it that they collide? And the bottom line of that model is that you can decompose that total likelihood or that total probability as a sum of the electron scattering with a constituent of the proton, say a quark or a gluon. And this, of course, I don't expect you to follow through all of these details, but my bottom line is here that this model gives you rise to a very concrete predictions. And if you look at the prediction that it gives in terms of the plot here on the right, is that the dependence of these data points with the x-axis q squared should be a constant. And these are experimental data. So this is just to tell you that QCD is a highly predictive theory, and furthermore, whatever deviations that you see at higher or lower values in the y-axis are also captured by essentially next leading order corrections in QCD. So, and this is what comes out of what's called deep inelastic scattering, and it's a cool example of the predictive power of QCD at high energies. Now, let me go back to what perhaps we're all more familiar with, which is QCD at low energies. And we know by experience that there are particles known as mesons, and there are particles known as baryons, which you can measure in scattering experiments. Say, to the right, mesons are pairs of a quark and an anti-quark, and baryons are essentially bound states of three quarks. At least that's the group theoretic way in which we understand them. And the puzzling thing here is that, as opposed to electrons, which you can also bind into bound states with, say, with a proton and form the hydrogen atom, you don't observe free quarks, but you can observe free electrons. And this is something that's understood, I would say, qualitatively to some extent, but it's not understood in full detail in terms of with quantitative control of the theory. So that's still an open question. And if you look at, say, it's curious that if you look at the masses of these particles, say the pion, it's about 135 or 100 or 140 MeV, and you compare with the masses of the constituents, say an up and a down quark, and plus gluons, they don't add up to 140 MeV, not even close. The up and the down quarks are both less than 10 MeV, and the gluons, if you took them to be non-interacting, they would be massless, and they wouldn't contribute much. So there's some rich dynamics which we don't yet fully understand, but we know it's right, but for reasons I'll tell you in a moment, that lead to these masses here, say for the pions and for the proton. Okay, so how is it that we can even do calculations with these? How do we calculate, say, scattering amplitudes between mesons and baryons? And well, actually, before going to that, let me emphasize why our usual method that we would use in field theory, which is perturbation theory, fails. And that's because if you take the beta function I showed you a few slides earlier and you essentially solve that differential equation for the coupling as a function of mu, you'll end up with this expression where the coupling constant is essentially, well, up to a square and factors of pi is proportional to, inversely proportional to a logarithm of a scale divided by, of the scale mu, which is the one that controls your, what you mean by the coupling constant, divided by a scale, which is a characteristic scale of the theory that you have to fix by experiment, which is called lambda QCD. And if you just look at this expression, and if you see and you'll see that when mu equals lambda QCD, this logarithm becomes 0, and therefore the whole coupling constant, as written here, will become infinite. And if you have an infinite coupling constant, then any perturbative expansion that you try to do will break down because you don't have control of your observable as an expansion on a small number. So what you usually do in high energies is to essentially expand in a power series of g squared. But what this is telling you is that if you take the external particles energy down to scales of this order, say lambda QCD 250 MeV, which is disturbingly around the scale of the masses of the pions and protons, you won't be able to use perturbation theory. And that's why what I showed you here on the previous slide, we don't have a nice understanding in terms of diagrams, at least in terms of QCD, in terms of the theory that I showed you earlier. Now, just for you to know, we do have theories which are called effective theories that are able to explain the dynamics of pions and protons or neutrons, essentially mesons and baryons as composite objects, but they rely essentially on you being at sufficiently small energies so that lambda QCD or in this case on this other scale, which is here f pi, the pion decay constant, is large compared to the typical energy scale that you're interested in your experiment. So, and what you're losing here is that you don't anymore have a description in terms of quarks and gluons. You have to essentially put in the particles that you observe by hand here. You write down the most general Lagrangian consistent with the symmetries that you can possibly write. And you end up to leading order with something like this. And it works. It really gives you very good predictions for low energy physics. But it's limited, well, just as the original perturbative formulation is limited to a specific energy range, which is what we can do so far. So just to emphasize something that I've maybe told you a couple of times by now, but QCD still has various deep mysteries. For instance, how does the mass of the proton emerge from gluons and quarks? The short answer is that we don't know quantitatively how that happens. There's a similar puzzle with the spin of the proton. So there are two ways in which you handle the proton theoretically. One is to essentially start in chiral perturbation theory, which is the theory I showed you in the previous slide, and put the proton in by hand, fix the parameters such that the proton has the mass that you observe. Of course, that will give you further consistency requirements on the other masses of the hadrons, but you don't have a description in terms of the underlying QCD theory. Or at high energies, you can essentially understand it as a sum of quarks and gluons, but that only works provided that the quarks and gluons in it, and therefore the proton itself, are highly energetic. So we still have a lot to do in this direction, and this is essentially what I want to tell you about, what I want to motivate you about QCD, that it's interesting. Now, before you ask, well, if you don't have that much quantitative or qualitative control, how do you know that all of these theories match up to each other, and how do you know everything is consistent? Well, theoretically, we could spend a couple of more hours essentially doing calculations and showing that that's the case, but I find it simpler to tell you that if you take QCD, you discretize space-time, and you essentially solve this field theory on a lattice, so you on a grid of discrete points on the computer, and you essentially calculate correlation functions of your operators, and you essentially look for what the masses of the hadrons are, and you fit to experiment, you get a very, very good agreement. So if you look at the plot here up on the right, the black lines are the values of the masses of the various hadrons obtained from experiment. The blue circles here are the masses that this paper used to essentially to fit the free parameters of your theory. And then the other red points with their error bars, which are due to computational uncertainties, are the predictions that you'd get from solving the theory from first principles on a discretized grid. And you see that they all match up and agree very well with what you see experimentally. So this is to say that we're very sure that QCD is the right theory. It's just that there are a lot of things that we don't know how to calculate, and we're working on that. And that's the motivating part of the story that should encourage people like you to jump into the field and start making your own contributions if you like this kind of story. Okay, as a summary then, just to tell you, so that you can see it from afar, here I've listed some of the energy scales in QCD, where you'll see that to the left, you have the low energy regime where essentially you're close to lambda QCD. And you can use chiral perturbation theory to some extent, depending on what observable you're asking. And for, say, for energies above giga-electron volt, you'll find that perturbation theory starts to apply. The degree to which it starts to apply is, of course, dependent on how precise you want to be with your measurements. But as you then start going to higher and higher energies, the traditional perturbative QFT tools start making sense. Okay, so this is my, I guess, 20-minute review of what QCD is. Now, I'll stop to ask for questions for a minute if you have some, but the next item on the schedule is to move to thermal QCD. So what happens if we put that complicated mass that I just showed you at finite temperature? I'll stop. Yeah.
So in lattice QCD, you mentioned that one of the outcomes are the masses.
Yes. Yes.
What else do you do in lattice QCD?
In principle, well, you can do a lot of things, really. You can, so the masses the masses of the light hadrons are particularly simple to extract because essentially, if you look at all you have to do is look at correlation functions and look at their decay at large energies. And if you know a bit about QFT, you'll know that the correlation functions, the 2-point functions of two operators, if they represent a particle, they'll go like 1 over the momentum squared, k squared, plus their mass squared. And then if you fit that to what you see, to the correlation function that you calculate on the lattice, you'll be able to extract the masses. So that's a particularly simple observable to extract. In general, you can calculate any number of any correlation function that you're interested in, with 2 caveats. One, you only get to do that in Euclidean signature for purposes of stability of your of your computation. Essentially, if you do it in Minkowski signature, the convergence of how the lattice calculation is technically implemented, which is essentially to calculate a path integral numerically, is poor. So that leads to what's called sign problems, and you can't really know for sure what their value is with confidence. There's a similar problem with observables that involve fermions in a non-trivial way. You also have what's called a sign problem, and people have worked on ways around that to do calculations and essentially to arrive at the spectrum for which you certainly needed to input fermions in one way or the other. But to come back to your question, in general, you can calculate any correlation function in the Euclidean signature. And the reason why that is, and if I am allowed to draw on the board, which I'm sorry for folks on Zoom, it's essentially because you're integrating over a set of fields. You have an action here, which has a minus sign because it's an Euclidean action. And then you insert here whatever operator as a function of the field that you want. And this would be essentially the expectation value of the operator in Euclidean spacetime. So you're taking for people who have heard of this before, you're taking the path integral of the theory, using it as a probability measure to average observables, and then just calculate the average. Of course, this is in theory, formally, this is an infinitely big. This is a space with infinite dimensions of variables, so you can't possibly hope to do all of them numerically. You have to discretize, and well, that's the reason why you have to discretize again. Yes.
Curious about the way they estimate these masses.
From what I hear, it's awfully similar to what I think you would use in your line of research. What you do to evaluate this is, well, after you set up your grid, you define at what space-time values you'll evaluate your correlation functions, you define what objects will you be taking expectation values of, and so on and so forth. What you do is you sample using Markov chain Monte Carlo, basically, from this distribution, and then you essentially you move around the distribution that this is giving you, and you follow through with the standard processes that you know more about than I do. No, that's mostly outdated by now. That people, and at least the people I know in Lattice QCD, and the people I know that do experimental searches for and experimental studies of QCD, Bayesian statistics has taken over by far by now. Yeah.
You have a question in
Yes.
the chat.
Yes, I have one. Are there any non-perturbative properties that could give you information about the proton and the neutron? Well, certainly. I mean, people, as I understand it, have also tried to calculate to some degree aspects of the proton or the neutron wave function with using these methods. And my impression is that they're not conclusive yet, because otherwise we'd probably all know. But people do that. That's one of the things that people are interested in doing. Okay, more questions? Okay, so let me move on to what happens if you take all of the mass that I just described and you put it at finite temperature. Okay, it turns out that the phase diagram of QCD has been studied for a while as well, of course. It's a question that people would ask themselves and they would like to give an answer to. What happens here is that most of these areas here in the phase diagram, which are essentially divided into 3 regions, one is down here, which is called a hadron gas, which is essentially what you'd get by taking all of the low energy hadrons and some of the higher energy hadrons, and you increase the temperature, and in the same way that, say, air heats up inside the room, you would also call it a gas, which has essentially very similar properties. Well, the difference is that they can interact among each other, but that's a detail compared to the difference of this phase with the phase up here, which is called the quark-gluon plasma, which is the high temperature phase of QCD. So the biggest difference between these two is that in the hadron gas phase, quarks and gluons are confined inside hadrons. And the quark-gluon plasma, all hadrons have melted, essentially. And you only have, and you can really talk about quarks and gluons as its constituents. You can't measure really a quark or a gluon because they're inside this hot thermal bath. But the way in which you would describe the system is in terms of quarks and gluons, and you do that rather effectively if you had the ability to do calculations. And so now mentioned down here, there's another phase which is called a color superconductor, which is conjectured to be present in the course of neutron stars, for instance. So at very high densities and not too high temperature, but at very high densities, very high pressures. And so here, if you look at these green lines that go down from the quark-gluon plasma to the hadron gas phase, these are what we understand that the current experiments of heavy ion collisions, which I'll get to in a moment, are doing and probing through this phase diagram. So here RHIC is the relativistic heavy ion collider at Brookhaven. And here you have the LHC, which at CERN, that also gives you some collider data of, say, colliding 2 heavy nuclei, say gold or lead. And by studying the outcomes of these collisions, you can essentially have a glimpse into what the quark-gluon plasma is. Another question that I'll not get to discuss in detail today is whether this phase diagram has a critical point. Theory universality arguments suggest that there is, and suggest that this critical point is in the same universality class as the 3D Ising model, for whomever understands those words. But experimentally, it's still not verified. We still have to essentially see the effects of such a critical point, and we also have to do the calculations to understand how or what would you see if a heavy ion collision gave rise to a quark-gluon plasma that, as it cooled down, passed close by this critical point. And so pictures, this is far simpler to understand than what I just showed you. So what we're thinking about with a heavy ion collision is that you have 2 atomic nuclei, which are here depicted as flat pancake-shaped objects because they're highly Lorentz contracted. So since they're at very large speeds, if you look at them from the rest frame of the lab, you'll see them to be very contracted along the direction in which they're moving. So let me give you a moment to watch the video. So what you see or what you expect in such collisions is that the 2 pancakes collide head on, and then some of them will fly through and you'll still see a high occupancy of gluons and quarks at the extremes of the collision. But on the middle, you'll see that, so let me play this again. In the middle, you'll see that at early times, a red region here appears, which essentially represents the quark-gluon plasma. And then after you let the system evolve, this plasma will become cooler and cooler, and will eventually freeze out into hadrons, and well, which would be pions and protons. And if you look at the time scale here on the bottom right, you'll see that this is measured in terms of Fermis or femtometers, which are 10 to the minus 15 meters. So the whole of this process as a whole takes on the order of 10 to the minus 23 seconds or so. So very, very fast. And well, now let me show you a few pictures that will make you far more comfortable with this than you will have been over the past half hour or so. So this process you can represent as, well, the initial stage is determined by two colliding nuclei. And after they collide, there will be some complicated pre-equilibrium dynamics, which will essentially describes how the collision between these two gives rise to a plasma with a well-defined temperature, chemical potential, and all the stuff you know about thermodynamics. After that time, which is a very, very short time, it's about 10 to the minus 24 seconds, you'll enter a QGP phase, and the plasma will start expanding because of pressure gradients. And then after, say, 10 more Fermi over the speed of light, you'll start hadronizing, and eventually particles will stop interacting because the system will be cooled down. And you'll see, in the sense, a very similar picture to what you'd interpret in the CMB, in the sense that you'll see fluctuations, you'll see regions that have slightly more energy, slightly less energy, which are determined by how the quantum fluctuations evolved at very early stages. And then after some time, if you wait, this is on the order of 10 to the minus 8 seconds. This 10 to the 15 here is to convert this femtometer into a meter. So after the particles fly for another meter or so, which takes them, since they're highly relativistic, it takes them about 10 to the minus 8 seconds. They reach the detector, and then you essentially measure the spectrum of what their energies were and what their momenta were. And from that, you get information about what was happening in the early stages of the collision. This is essentially what I'll try to describe in the final 10 minutes here. Okay, so this is, if you didn't get the analogy with the previous picture, this is what I meant. So in both cases, you have essentially an expanding system with initial state quantum fluctuations that give rise to all sorts of rich dynamics later on along the way. But they're very separated in terms of timescales. Well, this is essentially a summary of what I was trying to communicate in pictures in the last two slides, is that both the expansion of the universe and a heavy ion collision have a Hubble-like expansion, in the sense that different points that move on space or inside the plasma that are co-moving essentially have a distance between them that increases linearly over time. Both have a rich hierarchy of decoupling processes as the plasma cools down. So in both cases, you start with a complicated plasma, where everything is in thermal equilibrium, and then as it cools down, then different particles start to stop interacting or interact differently. And first, you'll see a chemical change types among each other after some time, and then later they'll stop interacting altogether, which we call kinetic decoupling. And I already mentioned that both of them have initial state quantum fluctuations that you can hopefully measure, hopefully see their imprint in the final state. An advantage of heavy ion collisions is that you can really repeat this experiment a lot of times, and take statistical measurements of what of how the initial fluctuations imprint themselves into the final state. Of course, the downside is that the theory along the way is we both know more and we know less. We know more in the sense that we're sure of what theory we have to use, so we don't allow much ourselves to go out of that theory, and therefore doing calculations is harder. And whereas in cosmology we have say dark matter and dark energy, which we put into the gravity equations regardless, but we still don't fully understand what they fundamentally are. Yes.
In this parallel, do you have a linear theory to describe these anisotropies or whatever it is? The analog. It's, homogenities. You do after a transient time, and so okay, perhaps this can answer your question. So a heavy ion collision, as we now understand it, can be this is arbitrary. There's an arbitrary decomposition, but still a valid decomposition, where you have several stages. So the first one is what is described by a color glass condensate, which is just after the protons and neutrons collided, you'll have large amounts of energy released in terms of gluons, which will make up flux tubes connecting the charged objects in your collision. I'll illustrate that with a picture. But then after this initial condition is set, you have an out of equilibrium process that draws you to hydrodynamics. Then in hydrodynamics, you can use linear transport equations to understand how fluctuations propagate. I'll go into slightly more detail into point 2, because here I've actually done some research myself. But the bottom line is that, yes, you do have linear transport equations, but they're different in different regimes. You can't really, we don't have a full unified description of all of these stages that works without us by hand turning them on and off, essentially. We have to connect them by hand as far as our ability goes. Okay, so this is the picture I just promised you. So after the nuclei collide, the picture that we have in mind is that flux, gluon flux, so chromoelectric and chromomagnetic flux tubes, which are essentially to say gluons, appear after the collision, and they're, because of aspects of QCD that I haven't discussed in much detail, they'll prefer to arrange themselves in flux tubes between the two nuclei, essentially. Then after that's essentially how the initial condition for the rest of the evolution is set. Now, after this stage, you have two possibilities, depending on what your temperature, the energies of the plasma is at the initial condition. So if because you could either start at very high temperatures, well above the QCD scale, or you could start very close to the QCD scale, say at about 300 MeV, and there you wouldn't trust perturbation theory. But so the tools that we have, or the tools that I like, I should say, are two. The first one is to assume, if you assume that the system is weakly coupled, then you can treat gluons and quarks as particles, and you can write down a kinetic theory that describes how these quarks and gluons scatter into each other and how they make up the plasma. And the other one is the case in which the system is strongly coupled. If the system is strongly coupled, then you can't identify gluons and quarks as free particles. You just have a fluid with some microscopic properties. And the best intuition we have to understand this system comes from holography, from ADS-CFT calculations. And the relaxation process in ADS-CFT because you're taking the dual of your field theory to be a gravitational theory, and finite temperature is realized as having a black hole in the middle of your space-time. The relaxation process is essentially how the black hole relaxes to a steady state. And these are called the quasi-normal modes of the black hole. And just to show you that essentially some pictures of what happens, but as a relaxation process from the out of equilibrium regime into a hydrodynamic regime. Say in kinetic theory, since I don't have time to go into details, I'll just say that both in kinetic theory and in AdS-CFT, theories with a gravity dual, you have an early stage dynamics essentially that drives these curves down to an attractor. So the kinetic theory attractor is down here. And the AdS-CFT, you also have an attractor down here that quantifies, in this case, the ratio between a pressure and energy density. What I want to emphasize here is that there are some emergent timescales that determine how the system becomes thermalized or hydrodynamics. On the left side, that is given by the relaxation rate of your kinetic theory, and on the right-hand side, it's given by the quasi-normal modes of the black holes in the dual field. Now, I think this is one of the last things I'll say because I think I'm mostly out of time. But one of the things that we have worked on over the past years is, well, how general is this? And how can you understand, say, these curves in terms of a simple description that you don't have to conceptually at least think too hard about what's going on? And one of the directions that we decided to pursue is what's called adiabatic hydrodynamization, which is essentially gluing the adiabatic theorem of quantum mechanics with out of equilibrium systems, where the big picture idea is if you have a time dependent, if you can write the evolution equation for your state, whatever that state is, in terms of a Schrodinger type equation, and if you manage to diagonalize this operator H and find the spectrum, if you find that it's gapped, then after a transient time, everything that will survive is just the ground state because it will be a superposition of exponentials of negative time times their energies. So after that transient time has passed, everything collapses onto the ground state of this description. And what's one thing, and just to show you that this is actually applicable, we did that explicitly for kinetic theory with a well-known but complicated collision kernel. And this is the first figure of that paper where we essentially start from an off equilibrium initial state in kinetic theory and let it evolve as towards the attractor, which it evolves on its own towards the attractor. And then we show that we can understand this in terms of instantaneous eigenstates of an operator that generates the time evolution. Okay, so now, how much time do I have?
I think you have like 10 to 15 minutes.
Oh, okay, then I don't have to rush that much. Okay, so then after the system has equilibrated, you can use hydrodynamics. We can essentially take a slightly modified version of the Navier-Stokes equation, but you can just think about them as the Navier-Stokes equation. And essentially, all you have to do is specify your variables of your fluid, say how the velocities of each fluid cell, the temperature, energy densities, pressures, and so on and so forth. But, well, to formulate hydrodynamics, you need one extra input from theory, which are the transport coefficients in these hydrodynamic equations. You need to know how viscous the fluid is, what the thermal conductivity is, etc. Again, here you have two approaches, which are the most widely used. You can either use thermal QCD perturbatively by doing Feynman diagrams order by order on the Kaplan constant and see what you get. Or you can use gauge gravity duality, ADS-CFT essentially. And the whole purpose of this slide essentially is to tell you that in holography, you get a very clean result for one of the transport coefficients, and well, some others as well, which tells you that the shear viscosity eta divided by the specific entropy is exactly 1/4 pi. And this is something that you can actually go and try to compare with experiment later. And as we understand them, experiments are not too far away from this, which tells us that the later stages of a quark-gluon plasma are somewhat close to the plasma that you can obtain by doing a gauge gravity duality calculation. Now, on the last bullet here, I want to mention that there's an intermediate regime where the temperature is larger than the QCD scale, but smaller than the masses of the heavy quarks, where you can use these heavy quarks, the charm and the bottom quark, as probes for what's happening in the plasma, because since they're more massive than the temperature of the plasma, they're not thermalized, and the plasma sees them as external objects. So, yeah.
Yeah, I have a question. In the last slide, you say use the gauge gravity duality. Well, it's very basic. It's very basic. Is just using like the usual statement that gravity is equal to 2 copies of the field, or like an ADS-CFT statement?
It's an ADS-CFT statement in this case. I'll give an example in the next slide of what I mean by that, but not for that specific case, but you'll see the picture. So one example, and again, this is biased because these are examples that I've worked on for the past year and a half or so. Well, not actually only on one of these. I've worked on the one on the left, and the one on the right is older. Essentially, it's the papers where people calculate this are 2006 and 2010, whereas this ones are far more recent, 221 and 222. So these are examples of the things that you'd have to calculate to get the transverse coefficients that you need for your hydrodynamic description. It's essentially expectation values of, well, thermal expectation values of, in this case, electric fields, addressed by what's called a Wilson line. And if you're interested, I can tell you more about what Wilson lines are and why we need them. In short, we need them for the result to be gauge invariant, but there's more to them as well. But still, this is what this is the type of object that you'd calculate, and for different operators sometimes. But this is one of the things that I have been doing, and I can tell you a lot more if you're interested in. So now to your question, what kind of ADS-CFT construction do we use to calculate these things? Well, there are more, of course, but the one I like best is this one here in the middle, that you can calculate the expectation values of Wilson loops. Wilson loops are, again, Wilson lines that are close onto themselves. I can tell you more about them if you're interested. And what this tells you is that you can calculate the expectation value of this operator by solving the classical equations of motion that a string obeys on a higher dimensional spacetime whose boundary conditions are set by the Wilson loop that you want to calculate. So what you do is you say, I don't know how to calculate the left-hand side, but I do know what the dual description is. I do know that that if I want to calculate the expectation value of a Wilson loop in supersymmetric Yang-Mills with 4 supercharges, the right gravitational dual is anti de Sitter space with a black hole in the middle with radius that defines the temperature of this at which the boundary theory, the Yang-Mills theory, is set.
Bruno,
Yeah.
I see
Yeah. Yes, don't, I don't see it.
Yes, are you there?
Are you talking about my raised hand?
Yes.
Okay, fine. Hi, Bruno. So I wanted to ask you exactly about the use of ADS-CFT in this context. So I have a general question is, it seems that people take seriously the gauge gravity duality in this context of quark-gluon plasma, or do you agree with that?
Yes, they,
Okay.
as a proxy of
That's
what.
nice.
Yeah.
But the question now is, what do you do? I mean, where is the CFT in the supersymmetry in all that discussion, right? Because you're not doing super young meals, right? You're doing just young meals. So how
Oh, in this case, I am doing super young mills. In this case, I am.
okay, sorry. Okay, fine. And the other thing I want to ask you is that you showed some transport coefficient that is predicted by holography, and you can measure it in experiment, and you say that it's not far off. Is there any other set of observables that you also? I mean, is there any contradiction that you measure or not?
Is there any contradiction, say, between the
From other observables.
prediction?
Oh,
So if
the
so
predictions of
the prediction from holography, you say?
right. Yes.
Oh, well, I wouldn't call them contradictions, but they're not perfect, if that's your question. They do not fit the data precisely.
But within error bars. I mean, they're not. You're not sure, right?
Yeah, the thing is that there, as far as we are along the way of understanding heavy ion collisions, because you have a lot of stages, it's hard to say which
Right.
to which part you would attribute the mismatch between theory and experiment.
I see.
I mean, you might be able to fit the data well with super young mills, but provided that you did something weird with, say, with the freeze-out process later on, which is also something that people model and discuss about. Or you could also have something strange going on with the out of equilibrium stage, which are not fully understood, really. So it's so what's done, as far as I can see, is use these things as baselines with which to compare. And then as theory improves, then we'll be able to say, well, to what degree they agree or disagree, assuming such and such. So,
All right.
yeah, the extraction of these numbers is not, it's not clean, and it usually relies on specific modeling that you need to do to interpret the data.
Oh yeah, of course that would be the case, but it's still interesting. I think that you use ADS CFT in this kind of QCD context. So yeah, that answers my question.
Yeah, well, we actually have many more reasons why we're doing this, even in super young mills, but they're technical, so I don't want to spend much time into them. But we can talk more about it later.
Sure.
Okay, so I believe I just mentioned the equality on the top of this slide. But now if you want to calculate correlation functions of field strengths, there's a nice formula that you can find in textbooks that if you take derivatives essentially with respect to the path that the Wilson loop goes over, what you get out of those derivatives are insertions of electric fields or magnetic fields. And again, that's something that's somewhat technical. I won't show you here, but you can from here not only calculate expectation values of Wilson loops, but also expectation values of electric fields stressed by electric or magnetic fields stressed by Wilson lines. Okay, so now let me just to leave on a happy note, let me again show you the video I showed you before, which is mostly about the stage that I described here, hadronization, which is essentially you take all those red regions and that essentially describe the plasma, and as you go further forward in time, they become more and more hadron-like, where you have, say, protons, pions, and other low energy particles. And then if you wonder where the detector is on this process, the detector in your collider would be up here or down here, or at the top or the bottom of the video, because the direction that's horizontal here on the picture is the direction along which you collided both nuclei. And one of the clearest indications that what happened is indeed the formation of a quark-gluon plasma is that the spectrum, say the momentum and energies of the particles that you measure at the detector here on the top and the bottom is thermal. It's well fitted to a thermal spectrum with a temperature given by something like 150 mega electron volt. This is an example of an event in the actual CMS detector, how they represent them, and just to show you how the data processing works, at least from afar. What interesting things to see are, apart from looking at the global spectrum that you'd see in all directions, you'll also get some things that are called jets, which are beams of collinear particles that are usually back to back here and here. And you can also, as well as heavy quarks, you can use them as probes for the dynamics of the plasma that was here in the middle. So again, and this is something that you can do more from the conventional high energy perspective, because these jets would be highly energetic beams that, because they're highly energetic, they'll not be thermalized along with the plasma, and their interactions will be different. There won't be hydrodynamics. There will be some more complicated things that you can use to constrain what the fluid is. Okay, so just to conclude, well, QCD is a very rich theory that we know that it describes our world, but we don't have full understanding of it yet. And to emphasize again why it's pressing to understand QCD, even if you're not interested in QCD alone, there are aspects of anomalies in the standard model that might yet very well be accounted for by QCD effects, such as, say, the muon magnetic moment. There's an anomaly in the standard model that essentially experiment measures it to be different to the naive prediction that you'd get from Feynman diagrams. And it turns out that the diagrams that are least under control are the QCD diagrams. It might very well be that if you go further along this direction, you'll get something that doesn't require new physics, but QCD explain it as well. And in any case, you still need QCD to assess the amount to which you need to correct the standard model with new physics or new particles. Again, a few weeks or maybe a month back, the CDF experiment reported that the W boson mass was off by something like 8 sigma from the standard model concordance of all the other experiments. And again, because of the way in which that experiment was set up, there are specific QCD observables that might interfere into how you interpret the data and essentially what finally the extracted value for the W boson mass will be. There are, shortly after the measurement, of course, there were papers addressing precisely this. The discrepancy went down, not all the way, but just a bit. And well, essentially, we have to continue doing calculations to see what happens later. And no, finally, to conclude about what I'm doing right now, which is heavy ion collisions. just to emphasize that this is a really cool experiment that allows you to produce mini universes where you see really rich and complicated dynamics all the way from the start to the end. And it really has a lot of potential to tell you more about the rules and the workings of QCD and what our world is, essentially. Thank you.
Thank you, Bruno. I think we have some time for a couple of short questions. So if anyone has one, please go ahead.
Going back to this parallel between
Yes.
do you have some analog to Gaussianity and non-Gaussianity when you measure
Certainly.
functions?
Certainly, they're not interesting in the same way as in the cosmology context. In the cosmology context, you'd usually use non-Gaussianity to, well, you either have late time non-Gaussianity, which you'd use to understand gravity, but you also, at least the kind of non-Gaussianity I worked with you on was primordial non-Gaussianity, where you essentially be probing for new physics. Here, you also have a kind of non-Gaussianity that you can use to search for new phenomena, specifically the critical point. That's something that I'm actually thinking about right now with my advisor, which is about how non-Gaussian fluctuations are affected, which there are non-Gaussian fluctuations because QCD is not linear, so you'll generically have non-Gaussian fluctuations. But these, since this process as a whole is an out of equilibrium process, these non-Gaussian fluctuations might be affected in a non-trivial way, but by passing close to this critical point. That's a very interesting question that we hope to address in the near future. Whether that is connected to the initial conditions, or whether you have essentially a type of primordial non-Gaussianity, the answer would be yes, but you don't expect to use it as a probe for the model itself. You expect it to use it to probe something along the way down the collision.
Any more questions? So I think I have one. When you're calculating these operation functions of closed loops, you're still doing it in lattice QCD or?
These ones.
Oh, okay.
No, I'm doing it. So in the bottom paper here is traditional perturbative calculation with Feynman diagrams, which hadn't been done at finite temperature, so we had to do it. I can show you the number of diagrams. It's about 20 or so. But,
Okay.
The reason why it's so many diagrams is because you have to insert gluons at the Wilson lines, and that gives you stuff to think about and spend some days doing some loop calculations. And then from the ADS-CFT side, you're just solving classical equations of motion. It's just a complicated partial differential equation. Very complicated nonlinear partial differential equation, but still something that you can pretty much just ask the computer to go ahead and do it. Of course, there are stability issues and convergence issues that you have to worry about because it's nonlinear, but it's more a matter of resources than of our ability to do it. We know how to do it. We're actually doing exactly that because they're nonlinear. They're complicated nonlinear partial differential equations. So we can only solve for this exactly in some limiting cases where you have symmetry essentially guiding us. In general, we have to solve the equation of motion for the worldsheet numerically and extract the number that we want to get the correlate.
Okay. Thank you. Any more questions? I think we're good on time. So let's thank again, Bruno. And thank you everyone for coming both in person and via Zoom. So take care. For those of you that are in person right here, we're going to have the pizzas upstairs. So that's it. Thank you everyone for coming, and hope to see you in the next seminar.